Hello everyone. This is going to cover some examples from lesson 9.4, okay? And what we have to keep in mind in this lesson and moving forward is that when we have a circle, you always want to remember that all radii are congruent, and I can draw the radius in any which direction that I want. And keep in mind that the diameter, which is a chord that passes through the center, is twice the radius. All right, that's one thing. And the next thing you want to remember from a prior lesson is that the shortest distance from a point to a line is the segment that's drawn from the point perpendicular to the line. So this is going to be important to us as we continue on with these examples. All right, so I'm going to clear this up. We're going to look now at example 1. We have if segment PS, that's one of the chords, is 12 units, and TR, which is another segment here, is 15 units, we want to find the measure of QR. Let me clear this up. If you look closely, we're missing one of the arc measures. We have all of the arc measures except for ST. So we're going to remember that the sum of the arcs is 360. We'll go ahead and set an equation up and then take some time to solve for x, and you'll find out that x equals 20. And from here, what you'll notice is that if x equals 20, you could take the sum of those two adjacent arcs, arc ST plus TP, and we can see that those two put together equals 70. And we know that if the two arcs are congruent, arc SP or PS if you want to call it, and arc QR, if they are congruent, those two arcs, then that means that those chords in there, chord QR and chord SP, those segments are congruent. So that would mean that if PS equals 12, then QR equals 12 as well. All right, here's the next example. You have in circle A, segment SQ is 12, segment AT is 8. Then you want to find PR. Now there's a couple of segments here that we can identify. SQ is a chord because it has endpoints on the circle. PR, the measurement of that segment that we want to look for, segment PR is a diameter, and we want to keep in mind that the diameter is twice the radius. In my diagram, I see a radius AR, I see another radius AS, and then I have the measurement of AT, but AT is not a radius and it's not a chord. However, AT, we are given that it's perpendicular. Notice the right angle. I'm going to zoom in on that triangle ATS. And what I'm going to do is I'm going to start to label ATS. I know that AT equals 8. I know that SQ equals 12. And if that radius or diameter is perpendicular to the chord, it's going to bisect chord SQ. So again, if PR is perpendicular to SQ, it's going to bisect it. So now the 12, we'll see 6 pop up, and I can throw that into my triangle. And now I can search for that radius AS. If I find the radius AS, that means I could find the diameter, which is what I'm trying to find essentially, which is PR. That's twice the radius. Now, if you haven't already noticed, this is a Pythagorean triple, but if you didn't, you would have used Pythagorean theorem. But notice it's a Pythagorean triple, and that segment AS, which is the radius, is 10, and that would make PR, the diameter, equal to 20. All right, next example. In circle O, now that's the center. If they name it circle O, O is the center. We have segment FL is 3, segment GO is 5, segment OP is 4, and we want to find HJ. Just take a look at HJ. It's a chord, and the radius or diameter, part of the diameter, part of the radius, right, is perpendicular to that chord. So HJ is going to be bisected. So that would mean that HP, segment HP, is congruent to segment PJ. Let's go ahead and fill in the measurements from the directions. FL is 3, and again, if I'm perpendicular, that means those segments are congruent. So 3 will pop up on GL as well. Then we have that GO, the radius is 5. So that means any radius in the circle is 5. Another radius I see from O to J, point on center to a point on the circle. So OJ is 5. Then you're given that OP is 4. And so we're going to zoom in on that tiny circle OPJ and try to find the missing side. You can see it's again a Pythagorean triple. You don't have to do any work on that. So we know that PJ is 3, and we just have to double that up to find HJ. And so HJ equals 6. All right, let's look at 4. I'll zoom in on 4 and then 5, 6. So number 4, sketch the circle with a radius of 17. So here we go, a circle with a radius of 17. And I have a chord AB that's the length of 30. Now, the diameter is twice the radius. So let me extend that line. I have 17, so the diameter is 34. And being that a chord is 30, it's shorter than the diameter. So I'm going to just put it underneath it. And so that's 30. That's the measure of AB. How far is the chord from O? Now, the shortest distance from a point to a line or even a segment would be the segment that's drawn perpendicular from the point to that line. So what we're going to do is draw that segment. We're looking for that distance measure. Now what we can do is we can draw another radius here. Take a closer look. I drew a radius right there and created a right triangle. I'm going to take that right triangle out of the circle, place the radius where it belongs, 17. 30 is bisected into 15, so that's going to pop up right there. And so we just want to find that measure of that light blue line. That's the distance from the center to the chord. So if you haven't recognized this as a Pythagorean triple, it's not as common, but you can do the work if you need to, and you're going to find out that it's equal to 8. So the distance from the center to the chord is 8 units. Okay, in number 5, we want to sketch circle O with a radius of 5 radical 3 and a chord XY that is 5 units from R. So when they give me the measure 5 units from R, from the center, that's going to be a segment that's drawn perpendicular to the chord. So here we go. I have the circle with the radius. I have the chord that is 5 units from R. So here's my chord. And here's me showing that I'm 5 units from center R, point R, which I have not labeled. So let's go ahead and label that. Okay. Let's continue this. I can draw a radius and create a right triangle here. Okay. And what we'll do is we'll take this right triangle out of the circle so we can zoom in on it. We've got 5. We have the radius, 5 radical 3. That's from right over here. Okay. And we have the measure. I'm using A on this leg only because X is being used in the diagram. So A. And we can go ahead and use Pythagorean theorem to find the missing segment A. Let's go ahead and do that. Get 25 equals 75. Do the work, simplify your radical, and you get 5 radical 2. That's the measurement of that small segment. And so what we want to do is we want to double it up because these measurements are congruent because the radius or part of the radius is perpendicular to the chord. So those segments are congruent. So our final answer is 10 radical 2. All right, here's number 6. Number 6 required a little bit of work. So redraw the circle larger than how it's drawn here, okay? So you can really get in that circle. We have that AB, which is a chord, equals 16. We've been told that CD is perpendicular to AB, so it's bisecting that chord. And we have that arc, BC is 60 degrees. They didn't show it here, but this is arc BC is 60 degrees. All right, so what we're going to do is go ahead and label. We're perpendicular, so the 16 will be broken up into 8 and 8. Okay, I'm going to go ahead and draw a radius. Well, let me put the 60 degrees on the arc here. And then we're going to draw a radius. And what you have here is a central angle. Take a closer look. Angle BOC is a central angle. I'm going to zoom in on that circle. Okay, that central angle is going to be the same measure as the intercepted arc, which is arc BC. So in this triangle, I've already got 8. I know that it's perpendicular. There's my right angle. I know that the central angle is now 60 degrees, and we recognize this as a special right triangle, the 30, 60, 90. And what we want to do is understand that if I can find the measure of OB, which is the radius, all I have to do is double up that measure. Okay, so sorry, it says triangle BOX. That's a capital X there, and then there's a small x on that hypotenuse. Okay. All right, so let's go ahead and do this, okay? 30, 60, 90. The side across from 60 is 8. That would mean that the side across from 30 is 8 divided by radical 3. And remember, you do have to rationalize, but I'll do that later. The side across from 90, which is what we're looking for, is double that measure. The ratio of the side across from 30 and the side across from 90 is in the ratio of 1 to 2. So this is going to be 16 radical 3. I'll rationalize that now because that's the number I need. And so I get 16 radical 3 over 3. That represents x, which is OB. And in my circle, go back to the original circle, segment OB is a radius. If we're looking for the length of the diameter, we double up that measure. And if we double up 16 radical 3 over 3, we get 32 radical 3 over 3. Okay, number 7, a plane P cuts through a sphere. So imagine a tennis ball, and I slice off part of the tennis ball. If you look at the tennis ball, it'll look like there's a hole, and it'll be the shape of a circle. So that's essentially what's happening here. And that little hole has a diameter of 24. The original sphere has a diameter of 36. And we want to find out how far that plane, which contains a circle, is from the center of the sphere. Okay? So let's go ahead and draw this diagram. So something like this is happening. I have a sphere I'm cutting through, and I cut through, and there's a circle at the top with a radius of 24, and the diameter of the sphere is 36. Okay? So again, if you're looking at the top view where the plane has cut off the top of that tennis ball, I'm looking in and I see a circle with a diameter of 24. So I'm going to take that image away just for a moment. We want to find the shortest distance, the distance to that plane. So from a point O to the plane, which is being represented right here, you can see by a line in my case, but really a plane, should be represented by a parallelogram here, okay? But anyway, I want to find the shortest distance, so I'm drawing perpendicular. What I've created is a right triangle. And so I'm going to keep in mind that the radius is going to be half the diameter. So now if I've been given a diameter of 36 for the sphere, I know the radius is 18. Since I'm perpendicular to the chord, which is 24 here, because the diameter is a chord, right? 24 is going to be cut in half as well. And I'll have 12, 18. And all I'm looking for is a distance from the center to that chord. We end up with this right triangle. You can go ahead and use Pythagorean theorem to figure out the missing measurements. Okay? So we're looking for x. That's my distance from the point to the plane which contains the circle. Okay, and lastly, we want to find the measure of x and y. What we want to keep in mind is if the radius is perpendicular to the chord, we've been going through this, it bisects the chord. So that means x equals 5. All right, and so let's take a closer look. Add up those measurements. 5 and 5 makes 10. So segment or chord AB equals 10. And now we see that EF has already been labeled as 10 as well. So if the chords are equal, then the arcs are equal. So that would mean that arc AB also equals 86 degrees because it's going to be congruent to arc EF. And from there, we also want to keep in mind that if this diameter is perpendicular to the chord, not only is it bisecting the chord, but it's also going to bisect the intercepted arc on the other side. So arc AB is being bisected as well. So I think of that chord, as long as it's perpendicular, the diameter is perpendicular to the chord, it's bisecting everything in its path, including the arcs. So we're going to take 86, divide by 2, and you have 43 degrees. Okay? If you have any more questions, just let me know.